Ladies and gentlemen, I'm Łukasz PAŚKO from Rzeszów University of Technology, Poland. I would like to present a study titled Deep Learning versus Machine Learning for Predictive Maintenance under Limited Industrial Data. The study compares two models, random forest and LSTM. The main question of the study is simple. When industrial data are small, irregular, and not perfect, is deep learning really better than a classical machine learning model, or maybe a classical model works better in such conditions? I will try to answer this question based on a cross-machine validation case study. This is the plan for the presentation. First, I will briefly explain the practical problem and the models used in the study. Then I will move to the research gap and the research questions. After that, I will spend more time on the dataset because the phrase limited data is very important here. Next, I will explain data preprocessing and models validation. At the end, I will present the results, limitations, and conclusions. Predictive maintenance is about using data to support maintenance decisions before a failure happens. It is different from reactive maintenance, where we act after a failure, and from preventive maintenance, where we follow a fixed schedule. In this paper, predictive maintenance is treated as a binary classification problem. The model must predict whether a machine failure will occur within the next 24 hours. So the model looks not only at the failure moment, but also at the period before the failure. The study compares two different model types. Random forest is a classical machine learning model. It builds many decision trees and combines their results. It is often stable and useful in industrial problems. Long short-term memory, LSTM, is a deep learning model for sequential data. It can learn from time order, so it looks natural for sensor data. But LSTM usually needs many good quality observations. This creates the main question. The problem in the analyzed case study is sequential, but the data are limited. So which model is more reliable here? The research gap is connected with realistic industrial data. Many deep learning studies use large and clean datasets. In practice, data from machines are often limited, irregular, or incomplete, and such a case was considered in the paper. The paper asks two research questions. First, which model gives better results for short-term failure prediction? Second, which model is more stable when it is tested on machines that were not used for training? Now I move to the dataset. This part is important because it explains the title of the paper. The dataset contains synthetic sensor data that imitate industrial machine data. It includes 5 CNC machines. For each machine, there is a 2-week operating period. The target variable says whether a failure will occur within the next 24 hours. The table shows that the dataset is imbalanced. Most observations describe normal work, while failure-related observations are much less frequent. The words limited data do not mean only a small number of rows. The limitation is broader. There are only 5 machines and only 2 weeks of data for each machine. There are only 8 failure events in total. The target class is imbalanced. The observations are irregular in time and include missing values. There are also long gaps caused by maintenance. These gaps are important because the machine is offline, so the gaps should not be treated like normal missing values during continuous work. The predictive models use several groups of input variables. The first group contains sensor measurements such as vibration amplitude, motor temperature, electrical current, rotational speed, and pressure. The second group describes the operating context, including operating mode, ambient temperature, and hours since the last maintenance. Operating mode has three categories: idle, normal, and peak. There is also date time information, and the target variable is binary. One means failure within 24 hours, and 0 means no failure in that horizon. Before modeling, the data had to be prepared carefully. First, missing values were filled by linear interpolation. Then the time gaps between observations were analyzed. Figure 1 shows that some gaps were much longer than normal operating intervals. Normal intervals were usually below 30 minutes. Gaps longer than 2 hours were treated as maintenance downtime. 10 such gaps were found. The data were then split into continuous operating episodes, resampled to 15-minute intervals, and the operating mode was one-hot encoded. The main validation method was leave one machine out, or LOMO. In each fault, one complete machine was left for validation. The other 4 machines were used for training. This was repeated 5 times. This is stronger than a random split. The model is tested on a machine that it didn't see during training. Standardization was also done only on the training data in each fault and then applied to the validation machine. This helps avoid data leakage problem. After resampling, the data were transformed into sequences. Each sequence covered 24 hours. Because the sampling interval was 15 minutes, one sequence had 96 time steps. After one-hot encoding, each time step had 10 input variables. So one LSTM sample was a matrix of 10 features and 96 time steps. Importantly, sequences were built separately inside each LOMO fault and inside each operating episode. This avoided sequences that cross maintenance breaks or use feature information, so it also prevents data leakage problem. This slide shows the main difference between LSTM and random forest data preparation. LSTM receives a sequence, so it keeps the time structure, 10 variables over 96 time steps. Random forest could not use this sequence format in the MATLAB setup used in the study. Therefore, the same window was flattened into one long vector. 10 variables multiplied by 96 time steps gives 960 features. So both models use the same information, but in a different form. The LSTM model used a sequence input layer, an LSTM layer with 80 units, drop out a fully connected layer with 32 units, and a final softmax output. The training settings you can see on the slide. Class weights were used because the data were imbalanced. The random forest used 200 decision trees and bugging method. The model settings were chosen in preliminary experiments and then kept fixed for all LOMO faults. Figure 3 answers the first research question. Both models have very similar accuracy, about 0.94, but accuracy is not the most important metric here. LSTM has higher precision, so it gives fewer false alarms. Random forest has higher recall, so it detects more actual failures. It also has a much higher area under ROC curve, close to 0.99. Additionally, the Wilcoxon sign rank test was used to compare the models. The test didn't show a statistically significant difference, but this must be interpreted carefully because there were only 5 faults during validation procedure. Figure 4 shows the results for each validation fault. We can see here how the models behave on different machines. LSTM changes more from fault to fault, especially for recall and F1 score. This is important because a model used in industry should work reliably on new machines. Random forest is more consistent across faults. This suggests that it generalizes better across machines in these limited data settings. Figure 5 shows standard deviations across the LOMO faults. Lower standard deviation means more stable performance. Random forest has lower standard deviations for most metrics. The exception is only precision. Overall, this supports the idea that random forest is more stable across machines. The LSTM results depend more on which machines are used for training. With limited data, this makes the model less predictable in practical deployment. So the practical message is clear. If the company wants to detect as many failures as possible, random forest is the better choice in this study. In many maintenance situations, missing a failure is more expensive than checking a false alarm. Random forest has higher recall and more stable behavior across machines. LSTM may still be useful when false alarms are very costly and precision is the main goal. So the choice is not only technical, it depends on the cost of false positives and false negatives in the company. The general lesson is that LSTM should not be chosen only because the data are time series. Data quality, data size, class balance, and stability are also very important for selecting the appropriate model. To conclude, the study has several limitations. The dataset is synthetic. It covers only 5 machines, 2 weeks per machine, and 8 failure events. Resampling to 15-minute intervals was necessary, but it can smooth some short-term changes. So the results should be treated as evidence from a controlled limited data case, not as a universal rule. In this case, random forest outperformed LSTM on most metrics and was more stable across machines. Looking ahead, we suggest validating these results on larger datasets and in real industrial settings. It would be interesting to see if LSTM outperform random forest when there is real huge dataset. We could also explore recurrent architectures or hybrid models that could be more robust than the random forest. Thank you very much for your attention.